Hello and welcome to this video on deriving the Marshallian demand function of a typical consumer. So in this video, we shall be seeing how we apply the Lagrangean approach to derive the Marshallian demand function, also known as the uncompensated or optimal demand function of a typical consumer. So let's assume a consumer has a Cobb-Douglas utility type function given as uxy. So we know it's a Cobb-Douglas because if you add the powers, it should be equals to 1. So it's a constant elasticity of substitution from function. So the consumer faces budget constraints with income M and prices of good X and Y given as PX and PY. So she has income M and the prices of the two goods as PX and PY. So we want to derive the consumer's Marshallian or uncompensated optimal demand function for good X or Y. So we want to use the Lagrangian approach. Now, the Lagrangian approach is that the Lagrangian function is a function of the equal to the objective function plus some lambda multiplied by the budget constraint. So this is representing lambda, which is money multiplier. It tells you the rate of money sensitivity to changes in the consumer's budget constraint. And budget constraint is the income equivalent to expenditure, while expenditure is the price of X paid for X and the price of Y paid for Y. So this could also be written as this. So the objective function is the utility function. So in that case, Lagrangian function will be X half, Y half plus lambda into all of this. So to proceed, you first find the first order condition by differentiating with respect to X, Y, and lambda, this, equate to 0. So you differentiate here with respect to X. So the power of X is half multiplied by X itself, half minus 1, differentiation rule, multiplied by Y half, since we are not multiplying with we are not differentiating with respect to Y, minus the price of X here as PX. So minus PX is a coefficient of X. So we have minus PX lambda, all equal to 0. So this is the first order condition. To write is FOC. But we can also solve this to be like this is X, half minus 1 is given as minus half, Y half all divided by 2 is equal to PX half. So minus half, the rule of algebra, it can also be written as 1 all over X half. So 1 times 2 will give you 2, X half. So Y half, 2X half all equal to PX half. So in that light, the consumer's next step will differentiate for L with respect to Y. So in doing this, it's same. So because the power of Y was half, so it goes to half, X half, Y half minus 1, differentiation minus PY, which was the coefficient of Y, lambda, all equivalent to 0. But again, from the consumer's and Lagrangian function, you can see that lambda has this as a coefficient. So you next differentiate with respect to lambda. So if you differentiate with respect to lambda, it gives you the budget constraint all again equivalent to 0. So you transpose these ones over where the 0 is. So it gives you pxx plus pyy. So the next step is for you to divide equation 1 by equation 2. So equation 1 again is given as this y half 2x half is equivalent to px half. And equation 2 is given as x half over 2y half equivalent to py half. If you divide both, then it's equals to px half over py half. So now p lambda cancels lambda, so it remains px over py. But this is division on division. So algebra states that division on division, in further division, turns to multiplication. So in becoming a multiplication, the numerator goes up and the denominator comes down. So you have this. But algebra also states that because they have the same base, the powers can be added. So 2 times 1 is 2. Y times y is y half plus half gives you 1. So this is actually 1, but we cannot write it as that. Divided by 2x, the same applies in this case. 2x to y, 2y over 2x equals to px over py. So 2 cancels 2, it remains y over x equals to px over py. So you cross multiply. This gives you pyy equals to pxx. Now this can also be written as pxx equals to pyy. So you substitute this equation 4 into the equation 3. Equation 3 is this. So where you see pyy, you put pxx there. So this was the case. So pxx plus pxx gives you 2 pxx equals to m. So but we want to solve for x rather. So you divide both sides by 2px, both sides. So 2 cancels 2, px cancels px. So what remains is x equals to m over 2px. So this is the Marshallian. So let's say demand for code x. So how do you know it's a Marshallian function? It has to be, not always, but it has to be at least a function of the price and income. So similarly, by substituting equation 5 into equation 3, we end up getting m equivalent to pyy plus pyy, because equation 5 is pxx plus, pxx equals to pyy. So you have m equals to 2 pyy. So you divide both sides by 2 pyy, it gives you y equals to m over 2 py. So this is Marshallian demand for good y. So therefore, the two Marshallian demand functions are x Marshallian is m over 2 px and y Marshallian is m over 2 py. So this is it. So look out for the other video on how we use the other approach to derive the Marshallian demand function using different utility functions.